teams. Great, I guess we can get started. I'm Ruth, and I'm currently studying at MIT, although I was competing with American Hive for quite a few years, and I did this event for like 6 years.
I'm Brady. I'm currently at Cornell. I'm part of the team that puts together our invitational here, and we've got an invitational coming up in a week, actually, so that's cool. And I only did this event for like 3 or 4 years, but I've been competing in Science Olympiad since fifth grade, so I don't know. It's my favorite event by far, so.
Yeah, and the event is Disease Detectives. We'll be looking at both divisions B and C, and this is part of the Georgia Tech Event Workshop series. All right. So we're going to get started by sharing the rules sheet and just going over some details from it. Then we'll be spending most of this time covering the difficult topics about this event. After that, we'll take a look at a few common questions. We'll give you guys a few tips and then share some other free resources that you can find about this event. And these slides will be shared after the meeting and so a recording of this.
Yeah, so this is the rules sheet. So just like any test event, the first place you want to start is looking at the rules and figuring out what you need to know. One nice thing about disease detectives is it stays every year, and from year to year, it really doesn't change that much. So once you learn it the first time, there's not a whole lot of extra learning to do from year to year. So it's split into three sections. The first one is background and surveillance, and this is a lot of the kind of basic information, a lot of the vocab, a lot of the kind of general big ideas of epidemiology, as well as surveillance, which is just how we figure out when there is an outbreak. The next part is outbreak investigation. This is my favorite part, and this is where you actually look at an outbreak and use what you know from this event to solve the outbreak. So you might get an example of an outbreak and have to calculate some values and say what the cause of the outbreak was. And then the last one is patterns, controls, and prevention. So understanding the patterns that these diseases can have, so like in graphs, epi curves, as well as understanding how to prevent them. So this often comes in kind of in parallel with the outbreak investigation. Often you'll use your skills to solve the outbreak and then figure out how you want to prevent it. And this event is not super conceptually difficult. The big ideas are all fairly simple. There's just a good amount of stuff to know. And like I said, once you learn it the first time, it doesn't really change that much year to year, which is nice. But there's a lot of different outbreaks, a lot of different situations you may need to apply that information in, and being able to do that and being adaptive on the fly is more important in this event.
All right, so let's go start with some difficult topics. And throughout this thing, if you guys have any questions, put it in the chat, put it in the Q&A, and we'll do our best to answer them as we go. So first off, we're going to look at studies, which, as Brady mentioned, is one of the big parts of this event. And it's how we figure out if there's an outbreak, what's causing it, how do we go about and try to prevent it from happening or try to control it as it currently is. So to do an outbreak study, you need to do a case study. And this is like the core of a lot of disease detectives tests. You are given a situation and then you have to apply principles from all three of the sections and the rules to it. For this, you need to use one of these types of studies. But then the question is, which study do you use? And how do you differentiate between all these different studies anyways? So you can see here is a couple categories, and we'll be discussing some of these in more detail. So two most important studies you'll be looking at are cohort studies and case control studies. So cohort is that you have a group, and then you choose some part of the population, and some of them will be exposed to some sort of cause, and some of them will not be exposed to something, and then you follow them over time to see who develops the outcome. In a case control, you start with people that are already either sick or not sick, and then you pick some people who are sick and some people who are well, and then you try to work backwards and figure out why the people who got sick are sick. And for case controls, here you have a bit of flexibility because you can pick 10 not sick people for every sick person, and this increases the power of your study, which is the ability to find an association if it exists. However, it also comes with the risk of introducing more bias, which is always a risk when you try to do stuff with studies. So usually you'll be given a situation and then you have to choose one of the two study types. And usually it's cohort versus case control. So if the population is very well defined, like people are at a family potluck, using a cohort study is probably for the best, because a cohort study, you can look at the entire group of people, see who is exposed, and then like figure out who got the disease and what caused it. But if it's impossible to identify everyone who was exposed to the agent, for example, if you're looking at a park and some people get sick from some sort of like random illness, you can't really track everyone who went to the park. So you just have to pick people who are sick and who are not sick, and then work backwards to figure it out. There's a couple of variations of cohort. The two big ones are prospective and retrospective cohort studies. In a prospective cohort study, as it mentions, prospective means looking forward. So you collect the participants before the outcomes occur. There's a couple of issues with this. The biggest one is attrition bias. So for example, if people who are more sick like drop out of the study because they have like comorbidities that are giving them other health issues, and they just drop out, then you're going to have a biased study. And additionally, a thing to note is that participants should not have the outcome at the time that you're collecting when you like originally pick them for the study, but they must be at risk of developing the outcome. So for example, you wouldn't pick someone who is not at risk of, like there's sometimes, like if someone is not at risk of developing a disease, like they just can't get the disease, you don't want to include them in your study because they're never going to have the disease. On the other hand, retrospective studies look backwards. So here, the outcomes have already occurred, but you're not picking the patients based on their outcome. So you're still picking the patients based on their exposure status, which you can use the records to determine. Of course, this introduces its own risk of biases. The exposure statuses may not have been complete because when they were collected, so maybe they didn't realize that you would be doing a study on it. But this is cheaper and easier than doing a prospective study, because some prospective studies go on for literally generations of people. So it's very expensive, very time consuming. Additionally, you might not have proof of the exposure status, which is also hard. You might just have to ask the people, and then people can like mess up in all sorts of ways with that. So those are the main types of cohort studies. There's a good amount of variations on case control studies. So first is matched or matched pair case control study. And matched just versus matched pair is just, a matched pair is you have one case for every control, and a matched is that you can have multiple cases for every control. In this case, for you carefully choose the controls to you choose the controls to have one confounding factor with the cases. So that way that confounding factor will be less influential on your study. For example, you choose controls like the same age as your cases. So that way the age doesn't confound the results. Next is a nested case control. So this takes cases and controls from a cohort that it's already done. So for example, if you have a cohort study, you're looking at some sort of genetic disease, but to know if someone like was exposed or had the gene for it, you need to do like a very expensive test. So you might want to do like a nested case control where you just take people who got the disease and people who didn't and look back and see who had the gene instead of like look at the entire population. Finally, there's case cohort. And this is also a case where you already have a cohort study, and then when you're done, you then add a case control study to it. So you compare the people who got sick in the cohort with a random sample of people just anywhere in the study. So this means that if person A got sick at the end, you might end up like comparing person A to person A when they were healthy during the study, which is interesting. So obviously we have all these great studies, but studies are imperfect, especially these are observational studies rather than experimental studies. So there's going to be all sorts of biases that we need to think about. The big one is confounding. So you probably have heard of this one. This is when there is a third factor that influences that's like associated with both the cause and effect you're trying to study. A famous one is like, for example, there was a study that was like, oh, coffee is associated with lung cancer. But the real association is that people who drink coffee are more likely to smoke, and smoking is associated with lung cancer. So the coffee wasn't causing the lung cancer. So this is something you control by randomized match control, all that kind of stuff. This is all on the SciOly wiki, and hopefully you have looked at it because that's very important for this event. Next is sampling bias, and one form of this is selection bias. So sampling bias just means like some sort of an issue where when you pick the cases, you pick it in a biased way. For example, one example of this is incidence bias, which is just people who have very mild or severe cases of diseases are excluded from the study. So if they're like super sick, they're on the brink of death, you don't include them, or if they barely have any symptoms, you don't include them. Like you're taking a very sampled section of people who have the disease. Another example of this is Bergson's bias or Bergsonian bias. And this mostly arises when you take a study from a population in a hospital. because people in a hospital are likely to have comorbidities and other health issues already. And then this becomes sort of like, these become confounding factors for the actual cause and effect you're trying to study. Finally, there's this interesting thing called Simpson's paradox. So Simpson's paradox, here's just a graph showing what happens. Like this is population A, this is population B. You can clearly see there's like a positive trend between X and Y in both populations. But then you put them together and it looks like there's a negative trend. So the question is like, how do you want to analyze this? Do you want to say there's a negative trend or are there positive trends? And here are some other biases you might encounter. So there's immortal time bias, which is a type of misclassification. This is when you assign a patient to an exposed group before they have been exposed. And this is a big part of cohort studies when you do the incidence calculation, because part of the incidence calculation is calculating like how the time between when they got exposed versus like when they got the case. So an example of this is if you're studying like survival time after heart transplant, you don't want to include patients who haven't yet gotten a heart transplant but will do so soon because they haven't like actually been exposed yet. Recall and response bias, these are kind of similar. It's like when the patient tells you the wrong information. One of them is when they remember wrong, the other is when they just lie. There's length time and lead time bias, which are more associated with screening. So length time bias is when you have a screening for a disease, but this like screening, you screen it like really early, you catch the disease, you think, oh, that's great, I'm going to start treating the patient. But in reality, you haven't really extended the amount of time they lived. You just told them they had the disease earlier. And lead time bias is something else where, like, if you have disease that progresses really fast, it goes straight and like goes straight to killing the patient versus a disease that like slowly kills the patient, but they're like the same disease. Your screening test might not catch the one that like kills the patient instantly, but it might catch the ones that kill the patients more slowly. So it looks like the patients who are being screened are doing better somehow, even though they're not. So a lot of very interesting biases can arise when you're doing studies. And there's a couple of less common stereotypes that are still good to know. A cross-sectional study it's like, as mentioned, it's like a snapshot in time. So you have a survey, you send it to people. You go like, are you sick? If you're sick, like, are you sick? What have you been exposed to? And then you send it back, and then you just do some analysis on that. And then there's also the ecological study, which is, here's a map. This is like John Snow's cholera study, which is very famous. This is like one of the origins of epidemiology. So you can see on this map that this is like the environment, the map of, I think, London. And here, Broad Street X is a pump. And then John Snow noticed that all the cases are right around here. And this is where he figured out that this is causing the cholera. There's something called ecological fallacy that isn't really completely associated with ecological studies, but it has the same name, so I thought I'd bring it up here. So this fallacy is, for example, if people in population A have a higher risk of cancer than people in population B, it doesn't mean that a single individual in population A has a higher risk of cancer than a single individual in population B. So it's just that a population's trends might not apply to the individuals. There's also time series where you just like look at different data points over a long period of time. This one usually doesn't come up. There's case series, which it's not really an analytic study because there isn't a control group. What happens is you follow a group of people with a certain disease over time. This is more to study like the natural history of disease. And finally, quasi-experimental and experimental studies are just ones where you control people getting exposed and not exposed. So the important thing is only experimental studies can really find causation. Other ones can find correlation, but like if we have strong enough evidence that the correlation probably is from causation, then we just like we're okay with that because we don't want to be infecting people with salmonella out here.
All right, so we've talked about all these studies. From these studies, we're going to get some kind of data, but how are we actually going to interpret that data? So we're going into our second topic here, which is the actual math part of it. And this event does have a lot of math, which can be surprising to some people, but we want to use that data and figure out if there's actually some sort of correlation between exposures and diseases, among other things. So the first thing we're going to look at is at the population level of disease, right? So prevalence versus incidence is something that comes up a lot and causes a lot of questions. So prevalence is going to be the amount of diseased people in a population. So the amount of diseased people in a population over the total population, right? So it is just a snapshot in time how many people are sick. And in this picture to the right here, which I like a lot, it's this bathtub, right? And the prevalence is all of the water that is currently in the bathtub, right? So that's all of the sick people that are currently there, while incidence is the rate of people getting sick. So that is your number of new people that are sick over the population over some amount of time. So like the amount of people who are getting sick in a month. And this can be represented as the water flowing into the bathtub, right? So every drop of water might be a new case. So your incidence is a rate of new cases, right? You also have mortality and morbidity, which are similar but not quite the same. Mortality is also a proportion, but a proportion of people who are dying, who get the disease. So the number of people who get the disease and die over the total number of people who have gotten that disease. And morbidity is a similar looking word, but pretty different. It's pretty much the same as prevalence. It's a bit weird, but realistically, it's just the amount of sick people over the total population. And then these numbers can be proportions. So like 0.0003, right? That would mean that that proportion of the population is sick if that's your prevalence, or ratios. And you'll often see diseases presented in this way that you have like 3 cases per 10,000 people. And these two numbers do represent the same thing, this proportion and this ratio. So you should know how to convert between those. Question, any formulas for these? There are, I mean, so like for prevalence, that would just be the amount of sick people in a population over the total number of people in the population, right? Incidence would be the total amount of people who get sick in, let's say your time period is a week. So the number of new cases in that week over the total population over your time period, so 7 days, and that would give you your incidence in cases per day, right? Mortality and morbidity are the same, where it's just something over the total population. So mortality is, well, actually not over the total population. That one's over the number of people who get infected, how many of them are dying. And then morbidity is the same as prevalence, really. So you can find those online too, but it's nice to have those formulas on your cheat sheet, but it can also help to understand them conceptually. If you just understand that prevalence is the proportion of people who are sick out of the total population, that might be more helpful than just having to look at your formula every time, but formulas can be helpful. So so now we're looking at correlation, right? So we do a study and we want to figure out if a certain exposure makes you more or less likely to get the disease. So we're going to look at a cohort study, and often you'll see information listed out in these two-way tables, right? So you have 2 columns, listeria positive and listeria negative, right? So on the left column, you have people who came down with listeriosis, right column, people who didn't come down with listeriosis. And then you have people who were exposed, ate the deli meat, and people who were not exposed, did not eat the deli meat, right? And this is inspired by the boar's head outbreak that happened like 2 months ago at this point, if you were wondering. But the way we interpret these is, so like the top left box would be, there are 5 people who got listeriosis and ate the deli meat, right? And it can often be helpful to sum up these columns and rows. So you can see in this red text, those are the sums for 6, for example, would be the total number of people who got listeria, right? So there are 5 people who got listeria and ate deli meat, 5 people who got it and didn't. So that's 6 people in total who got listeria. And then we can add all of those numbers up on the bottom or on the right and see that we have 81 people total in our study. So now when we're calculating risk and relative risk, so these are pretty related. Risk is going to be, I find it easiest to think of it as like a probability of, if we take any of the people who ate deli meat or had the exposure in this study, what is the chance that they would have listeria? So what proportion of the exposed people came down with the disease? So that would be 5 as the number of people who ate it and got the disease over the total number of people who ate the deli meat, which is 35, right? And that gets you a value of 0.143. And then we can calculate the risk for not eating the deli meat as well. So that'll be similar thing, 1 over 46 is 0.022. And the higher this number is, the more correlation there is. But we can't really tell correlation just from the risk, right? Because if we know the risk for eating deli meat is 0.143, that doesn't tell us much because the risk for not eating the deli meat could be much higher than that. And that would actually imply a negative correlation. So the way we sort that out is we calculate the relative risk. And all we're doing is we are taking the risk for being exposed and we're putting that over the risk for being not exposed. So we do 0.143 over 0.022 and we get 6.5. And the way we interpret that is those who ate the deli meat, so those who were exposed, were 6.5 times more likely to develop listeria. So 6.5 times more likely to get the disease. So interpreting this at the base level, so if the relative risk is 1, that means the risk is the same for being exposed and not exposed, which means there's no correlation. If it's less than 1, then that means that there's a negative correlation. So that actually means being exposed makes you less likely to get the disease. And if it's greater than 1, being exposed makes you more likely to get the disease. Okay, so we're going to look at the same two-way table now, but pretend that we have a case control study. So it's important to remember that we can't do relative risk on a case control study, so we'll get back to that in a little bit. But our preferred number here is going to be the odds ratio. So we have the same table, we can add things up in the same way, and then to calculate our odds ratio, we will take the odds for the diseased as well as the odds for not getting the disease, right? Yeah, there we go. So an important thing to remember is case control. We're starting with the cases and the controls, right? So we want to tackle the odds for the cases and the odds for the controls, right? So yeah, I think that was something slightly wrong on that. It should be odds for if you have listeria and odds if you don't have listeria. But the odds calculation is somewhat similar to the risk, but you're going to take for listeria positive, the number of people who ate deli meat over the number of people who did not eat deli meat. And that gives you an odds of 5 of having been exposed given that you got listeria. We can do that same thing for listeria negative and put those two odds over each other to get our odds ratio of 7.496. So very similar to the relative risk, we're just using odds instead. And the way we interpret that is those who develop listeria are 7.5 times more likely to have been exposed, to have eaten the deli meat. So it's important to see that distinction. It's kind of backwards from the other one, right? Where this time you're starting from developing listeria and seeing how likely they were to have been exposed. So here are your total formulas here. So if you just want to have the formulas, here they are. Relative risk should be pretty much what we talked about. Odds ratio, you can simplify that formula to AD over BC. And be careful with this table because if, for example, you switch the listeria positive and listeria negative, the positions of A, B, C, and D are going to switch around. So I think often it can be helpful to not use the formula and just understand conceptually how these calculations work, because it can be kind of difficult if it's not exactly presented to you in this way. So a little bit more about these two calculations. So odds ratio can be an approximation of relative risk given that an event is rare. And also if there's no correlation, then they're both going to be 1. And another important thing, so we have to use odds ratio for case control study, right? We cannot use relative risk. And that's because when we're calculating the risk ratio, we're taking the number of people who got, we need the number of people who got sick, who were at risk, over the total number of people at risk. But we don't know the total number of people at risk in a case control study, right? Because we just chose some amount of people who were diseased, some amount of people who weren't diseased. This is fairly arbitrary. So we don't know in total in the population how many people were at risk. So we can't calculate the risk ratio. So we need to use the odds ratio, which has slightly less power statistically, but is still useful. So those two concepts are the ones you'll see the most in disease detectives, but there are some others that come up. So the reproductive number is the number of infections produced by a typical infected individual. And that's estimated to be around 4 for COVID. So that means one person with COVID is expected to infect 4 other people. And that's on average. You can contrast that with the effective reproductive number, which is RT, and that considers the susceptibility of individuals. So if a lot of the population is vaccinated, then they're going to, instead of infecting 4 people, infect a little bit less than that. So your formula for that is RT equals R naught times X, where X is the proportion of the susceptible individuals. So if half of the population is vaccinated, that means that only half of the individuals are susceptible, which means that your RT is 2. So somebody in a population where half of the people are vaccinated is only expected to infect 2 people. We can also use this number to calculate the herd immunity threshold, and this is the amount of vaccination, so the proportion of the population that needs to get vaccinated in order to stop the proliferation of the disease. So if you reach the herd immunity threshold, you will get a stagnation of cases or a decrease in the number of cases. It doesn't necessarily mean you get no new cases. It just means you're getting people getting better more than they are getting sick, right? And that threshold can be calculated by 1 minus 1 over R naught. One thing that you'll see on studies a lot is a confidence interval, and that shows a likely range of values for some number. So you can see at the bottom, I have a example of some data from a paper, and at the right there, it says the odds ratio is 1.15 with a confidence interval from 0.71 to 1.87. So you can see kind of a representation of that at the top right, where we have these 2 different values. One of them is lower, but has a smaller confidence interval. One of them is higher and has a higher confidence interval. So if we have a smaller confidence interval, that means we are more confident that our true data is somewhere close to the data point that we measured. And the way we interpret this 95% confidence interval is if you did this study over and over and over again, 95% of the time, the confidence interval that you report will include whatever the true value for that number is. Good to move on. So one last topic to talk about is sensitivity and specificity. So this comes up when you're looking at tests for diseases. So at the bottom, I have a table here with a rapid test and a PCR test. So we're checking the how correct this rapid test is. And we're comparing it with the PCR test, which we'll assume is 100% correct. So that's kind of our baseline. If they're PCR positive, we'll assume that they actually do have the disease. So how do we measure how correct this rapid test is? So the first one is sensitivity. So that's the chance that a diseased person will get a positive result. So that's your true positive over true positive plus false negative. So if someone is diseased, how likely is it that they will correctly get the positive result from this rapid test? And specificity is the chance that someone who is healthy, so not diseased, will get the correct negative result. So that's true negative over true negative plus false positive. And one thing to remember is that these 2 values do have some sort of implicit trade-off, right? So this can be adjusted based on whatever test's threshold value. So if you have a high threshold value, so let's say you're measuring some amount of viral particles, and you have that level of viral particles necessary for a positive result very high. That means a lot of people are going to be receiving a negative result, which means you're going to be getting a lot of true negatives. So your specificity is going to be very high. But by bringing that threshold up, you're going to be missing a lot of people who do have the disease, and those people will be getting false negatives. So your sensitivity is going to be lower. So by adjusting this threshold value, we can change our sensitivity and specificity. And we might want to do that based on the nature of the disease, right? If it's a disease that's really virulent, like, I don't know, Legionnaires, for example, has a pretty high mortality. You want to have a test that's very accurate and doesn't let people who have the disease go back into the public, right? So in that case, you want a highly sensitive test. But if it's something like the flu test, where that doesn't matter as much, maybe you want a more specific test.
All right, so moving on to the final topic, which is trivia. And I know what a lot of you are thinking. The rules explicitly state that non-specific diseases should not be tested for this event. So why are we going to look at trivia? Well, a lot of times tests will expect some level of background knowledge for things not stated in the rules. Like, for example, how pathogens work, some common diseases that you'll see, that kind of stuff. Tests may ask for examples. For example, if a test says, can you name some pandemics in the past, like 500 years, would you be able to name one? So these are some good things to know or have on your notes if you have room. So first, I'm going to talk about some foodborne illnesses you should know, then some history, and then vector-borne diseases, and then just general pathogen knowledge. So studying these shouldn't be your first priority. You should already know all the stuff we covered earlier and all the stuff on the rules first, all the definitions, the stuff on SciOly wiki, that kind of stuff. You don't need to know any of these in details. Usually you just need to know a little bit about them. So first, foodborne illness and food safety. So this often shows up on tests because it is like a very interesting and pertinent topic. Just recently there's been so many foodborne illness outbreaks. So first of all, know which foods are associated with some common illnesses. For example, salmonella is usually like eggs or something. Listeria, like the one recently, deli meat, soft cheeses, that kind of stuff. And here are some good ones to know. Salmonella, which is one of the most common foodborne illnesses. Norovirus, which is very contagious. E. coli, Shiga-like, and non-Shiga-like. Listeria, Campylobacter, and then these are all a little bit less common than the rest. Campylobacter, Cryptosporidium, B. cereus, Shigella, Giardia, Trichinella. And on the test, if you're not sure, it's usually Salmonella or E. coli. So next is history. So this is explicitly part of the rules, although they don't really go into specifics on how much detail you need to know. Still, I think it's good to know about like some of the major pandemics in history. I think the 5 major ones everyone talks about are the plague, HIV/AIDS, SARS, COVID-19, influenza. And there's something common about all these diseases. And I'll just spoil it for you guys. It's that all these diseases are zoonoses. And there's a lot of interesting theories on why zoonoses are more virulent. One of them is, for example, like SARS and COVID-19 originally came from bats. And bats have a far stronger immune system. So that when they jump to humans, they're like destroying the human immune system. Some of the other theories are like maybe it's something to do with mutation, that kind of stuff. There's other diseases that aren't pandemics but are still very historically significant. For example, tuberculosis, which is this little cute video by Kurzgesagt here, covers it very well. Cholera, which was what John Snow studied, and smallpox. And smallpox is eradicated, so you should know about it. Although, yeah, you should definitely know about it because, and just in general, any disease you have a vaccine against, because this is like the only human disease we have eradicated. Now, some malaria. Yeah, these are diseases that often affect places that do not have as good health infrastructure and do not have like sanitation and that kind of things. You also might want to know some non-infectious diseases, like for example, the 4 big pollution diseases of Japan. That's like heavy metal poisoning, a lot of them. And some important studies to know are like John Snow's cholera study. Oh yeah, these are links by the way, in case you guys, and then these are videos you can check out later if you're curious. Some important studies to know are John Snow's cholera study. That's the one we talked about earlier. So that's the one where he realized that, a lot of people in this area are getting cholera. So he mapped it. He noticed that there were a couple of things. Like there was this one brewery where nobody was getting cholera. That's because they were taking water from somewhere else. There was another place where far from the pump where people were getting cholera because they liked the water from the pump for some reason. And then he traced it to there was a baby with cholera whose diaper was thrown into the water near the pump. Another one is Dallin Hill's British physician study. This was interesting because this was done back when people still believed smoking was okay for your health. So Dallin Hill, like this is a hill from Hill's criteria actually. They rounded up a bunch of like British doctors and then they just did a study and found that smoking does cause lung cancer. So this is pretty significant. There's this entire page the CDC has on the history of epidemiology that might be interesting to check out. There are some other people like William Farr, that kind of stuff. I think those are all on the SciOly wiki as well. So next is vector-borne diseases, and I'll start with why we care about these. They're a significant cause of human morbidity because they, like, especially if they can be spread by bugs. Bugs are kind of hard to control, so they can spread very easily. They have a very big impact on communities that lack sufficient healthcare resources, especially like malaria. And finally, climate change is predicted to make some of these more prevalent. Just yeah, in general, I believe like the kissing bug is expected to get more prevalent, ticks, mosquitoes, all that kind of stuff. So for mosquitoes, there's malaria, which is this picture here. It's caused by this parasite, and then it infects the red blood cells. There's also dengue fever, which is a virus, and Zika virus, which it doesn't cause like disease in healthy humans, but it does cause birth defects. You might have heard of it like a couple of years ago. Ticks are like tick diseases are pretty common to hear about in the United States, so you should probably have heard of some of these. There's Lyme disease and Rocky Mountain spotted fever. And some other ones are, as I mentioned, Chagas disease, which is caused by the kissing bug, and sleeping sickness caused by tsetse fly. These are interesting because Chagas disease has an acute phase and a chronic phase, and then the chronic phase can cause like heart failure, other all kinds of issues. And finally, in general, pathogens. Oh my god, I did not finish this slide. I'm sorry, my bad. I will finish this part. So viruses, the most interesting to note is that there's two main kinds of viruses we care about, retroviruses, and I think the other kind, I forgot what the other kind is called. I will look it up and put it in here. But the reason this is interesting is normally viruses, they inject their DNA into your cells get turned into virus making machines, you release all the viruses, then the virus spreads through your body. Retroviruses are a bit sneaky. They put the DNA into your cell's DNA, but they don't activate. So this is something like HIV/AIDS is like the most famous retrovirus probably. So there's just cells in the body that just have the virus's DNA, but aren't making any viruses. So one day, let's say if you thought you cured all the viruses, one of your cells can pop back up and start making the virus again. There's bacteria, and for bacteria, some of the interesting things to know is that they can be gram-positive, gram-negative, or have nothing. So gram-positive and negative just refers to how they stain with the gram test, and I believe they're susceptible to different types of antibiotics, which might be interesting. And the ones that are gram-none are especially interesting because that usually suggests they have something going on with their cell wall. And also antibiotic resistance is a really big topic because antibiotics are our best line of like defense against, well, offense against bacteria. But because of the overuse of antibiotics just across the board for treating disease, for agriculture, everything, a lot of bacteria developing antibiotics to one or more of like the antibiotics that we have. And this is predicted to be a pretty big issue, and you might see this on some tests. There's also parasites. So parasites, you have the macroscopic ones like worms like dracunculiasis, or the microscopic ones like malaria. And I think in general, these are a bit less common to see on tests. Prions, you should probably know what they are. They're like these proteins that corrupt other proteins and just like kind of spread themselves. They often cause neurological diseases. And the most famous one is the UK beef bovine spongiform encephalitis / transmissible spongiform encephalitis outbreak. Finally, there's fungi. You probably will basically never see this on tests, and it's most dangerous to people with weakened immune systems. All right, we're going to move on to some common questions we found on past YJI exams, tests in SciOly Wiki, and a test from Mitso.
All right, so this first one we're going to look at is an example of a case study. So we're looking at this outbreak in the Disease Detective Academy. So we have two questions here we want you to look at real briefly. So the first one is writing a case definition. So remember your person, place, time at triad for this, and try to think of some sort of case definition. And then also, what type of study are you conducting? So think of the cohort studies, the case control studies, and the other ones that we talked about. So I'm going to give you all probably just like a minute here to think about this for a little bit, and then we will go through the answers.
Yeah, if you have any thoughts, put it in the chat. Let us see like what you guys are thinking.
All right, I think we can start looking at the answers. So first of all, a case definition. So when we're looking at a case definition, we want to think about the person, place, time, right? So the person would be the kind of person that is infected and the symptoms that they'll have. The place is where the disease is happening, and the time is the time frame that we're considering. So the reason we want a case definition is we want to understand what cases we actually want to count in our outbreak. So there might be a salmonella outbreak in a certain food, but we don't want to count salmonella cases that are unrelated to this food, right? So for this outbreak, we want to define our people as people who experience these symptoms of diarrhea, fever, and stomach cramps. It would be nice to have a positive test or something, but we don't have that here, so we're just going to define that symptomatically. Our place, which is the Disease Detectives Academy. So those people who are at the Disease Detectives Academy on that date of August 3rd, 2022. So you might want to say that we're there on that date and contracted symptoms in some time frame, maybe like two weeks out from that date. And then looking at the type of study, so we looked at participants with and without the disease. You might see that that's familiar. Participants with would be our cases, and participants without would be our controls. So this is a case control study because we have divided our population into people with the disease and people without the disease, and then we will look at their exposure. So here is an example of data from this outbreak. So we have 2 exposures, sweet mango and fumed mushrooms, and we have a table that is sort of similar to a two-way table, not quite, so be careful with that. But we are tracking whether they got diseased and whether they ate that food. So first, we want you to calculate the risk measure for those 2 foods. So think about which risk measure will be best here, odds ratio or relative risk. Think about what food caused the outbreak and 3 ways to prevent future foodborne illnesses. And probably just going to give you a short amount of time to think here because I want to get through the rest of the questions, but try to see if you can calculate these numbers. All right, let's look at the answers now. So if you could hit to the next slide. So here is our odds ratio calculation. So remember, we want to look at the odds for the case and the odds for the control. So our odds for the people who got sick would be 82 over 41. Our odds for the people who didn't get sick would be 17 over 69. and that gives us an odds ratio of 8.118 for the sweet mango. And this is over 1. It's pretty significantly over 1. So this is pretty high correlation between getting sick and having eaten the sweet mango. And then if we do that same calculation for the steamed mushrooms, you should get 0.849. This is much lower and it is less than 1. So this is actually a negative correlation. So when we're looking at what likely caused the outbreak, that is going to be probably the sweet mango because it has such a high odds ratio. And one thing to consider is there can be some confounding. So it's not necessarily the case that like eating the steamed mushrooms, for example, makes you less likely to get the disease. It's probably just that the people who ate the steamed mushrooms were less likely to eat the sweet mango. And then 3 ways to prevent future foodborne illnesses. There's a lot of ways to do that. You can store your food more effectively. You can make sure you wash any sort of tables or anything after handling things like raw meat, and make sure that you store your food in the safe bacteria range, which I think is around like 40 to 60 degrees is at 40 to 100 is kind of like the danger zone of
I think
storing
it's 40
food.
to 140 is a danger zone.
Yeah. So making sure that you're either keeping your food cold or hot when you're storing it.
Also, just a quick note, I think this one was supposed to be 17 probably. It's like,
Oh,
it doesn't
yeah,
change the
true.
fact that mango is still more, but yes. We will fix
Yeah.
that in post.
No, the calculation is still right. I'm pretty sure. It's just that 41 is supposed to be a 17. But I think the number 8 is still correct for the odds ratio.
Okay, that's great. All right.
All right.
So next,
So we have.
yeah.
Oh, yeah. Do you want to take this?
Oh yeah, sure, I can take this one. So next we have some vocabulary. So we'll just pretty quickly go through these. So Dahl Hill conducted a prospective cohort study that demonstrated a link between smoking and lung cancer. So the question is this descriptive epidemiology, analytic epidemiology, or public health surveillance? So take a moment to think about it. We'll probably go pretty quickly because we want to save some time for questions. So this is going to be analytic epidemiology. It's not descriptive because they are trying to describe a situation, but they're also like doing a cohort study, which is analytic, and they're not really doing surveillance. So after feeling nauseous and abnormally fatigued for 2 days, he goes to visit his primary care physician, and he's exhibiting signs, symptoms versus sequelae. This is a little bit more on like the medical side of the vocab, and it's a good reminder that all these things are different. And in this case, the answer is going to be symptoms, because signs refers to like biological indicators like high blood pressure, low blood sugar, that kind of stuff. Symptoms are things that you more feel, like nausea, fatigue, malaise, that kind of stuff. And sequelae, if you've heard like post-COVID sequelae, I think these refer to symptoms that come like after disease is technically over. And next is 55% people infected with symptomatic people infected with dragonpox will die. 20% of the symptomatic people infected with dragon flu will die. Dragonpox is a higher than dragon flu. And then the words are infectivity, pathogenicity, and virulence. So take a moment to think about it. And the answer for this one is going to be virulence, because virulence refers to the severity of a disease. And the other two, infectivity refers to more how easy it is to spread. Pathogenicity is how likely you are to develop symptoms once you're infected. So next, Amir went to a party yesterday and learned that someone else tested positive for COVID-19. He doesn't have symptoms, but he goes to get tested and stays in his room while he waits for his results. And this one is, so there's some control, isolation, or quarantine. And this is going to be a quarantine because isolation only applies once you actually are confirmed to have the disease. Before you have the disease, you are in quarantine. So next is zero cases of neonatal tetanus in the US due to efforts in promoting the tetanus vaccine in pregnant women. So the words are elimination, eradication, extinction. For this one, the answer is elimination because it's in a specific region and there are no more cases. It's not eradication because there's still cases elsewhere in the world. It's not extinction because tetanus is not extinct yet. Next is a bat enters the church through an open window and bites a girl, giving her rabies. The bat is a fomite, bacteria, or vehicle. So let's think about this. So in this one, the bat is a vector because it is a living thing that's spreading the disease to a human. A fomite refers to an inanimate object, like a blanket, for example. And vehicle, it also kind of refers to an inanimate object, but usually we mean something like food. So the VAERS system is a national surveillance program where anyone can fill out a form to report a health issue post-vaccination. And is this passive, active, or sentinel? And this is just a classic, like, what type of surveillance is this? This one is passive because anyone can just fill out a form. You're not like calling people, going like, "Hey, you got a vaccine recently? Did you get sick after it?" No, they're telling you that they got sick. It's also not a sentinel because sentinel means like monitoring a few maybe specific hospitals that might be key indicators of how many cases there are.
Did you take the DAG? I'm not super
Oh, of
familiar with
course.
these.
Yeah, of course. So this is from MITSA 2024. So the following is this DAG, which is, yeah, I think this is like a new part of the rules. I didn't see it when I was competing. So these are like the risk factors for colon cancer. So you can see like these arrows point to high red meat consumption causes high fat consumption, also causes colon cancer. And these are only like dietary risks, as you can see. So let's say you wanted to only look at high sugar consumption. So why would it be important to control for high processed food consumption? And yeah, since I don't think I wrote down the answer, but the answer is because, oh, okay, yeah, there you go. High processed foods, you can see there was an arrow between high processed foods and high sugar consumption. This is because high processed foods have a lot of sugar in them. So if you include people in the study that also eat a lot of like processed food versus not a lot of processed food, they're going to have some confounding factors. So a DAG is really good for seeing like these confounding factors. So redraw the DAG with the minimally sufficient from 5, this question, with minimally sufficient adjustment set, we were only interested in high sugar consumption. Use boxes for controlled factors and circles for factors you are not controlling. You can ignore the risk factors of colon cancer that were not part of your original study. So this one, I'm going to go to the answer just because I think we're starting to run out of time. So here we have colon cancer and high sugar consumption, and these are deconnected because they're the ones that we're like looking at. And we're not adjusting these because if you adjust for high sugar consumption or colon cancer, you're kind of messing up your study. However, we do want to adjust for everything else because everything else can cause colon cancer, and we don't want any of this like confounding factor going on. So we will control everything else, and then we will not adjust these two. All right, finally, we have some just general tips for you. So you should know the basics from SciOly.org wiki and your vocab, or at least have your cheat sheet. Try not to miss out on the free easy points. Next is that you should do practice tests, which I think is the most effective way to study. So try doing all the non-trivia questions without your cheat sheet, just because, as Brady mentioned, things like the odds ratio and risk ratio, you should really have it memorized conceptually, so you should be able to do it without a cheat sheet. There's not that much foundational knowledge in disease that's like most of it you can memorize. So most of the cheat sheet should be dedicated to disease trivia, vocab, things like Hill's criteria, Coach's postulates, stuff that you don't really want to memorize, and possibly statistics. Oh, I was going to make a chart of like how much of your cheat sheet should be dedicated to each, but that's not super important. You can decide what's important to you. Here's a common trivia question I see people get wrong a lot: is you should not use antibiotics for viral diseases. Like that's going to cause antibiotic resistance. As we mentioned, that's a pretty big issue. Additionally, you shouldn't use it for Shiga toxin producing E. coli because it causes this really bad side effect called HUS. So just don't mention antibiotics if they're talking about Shiga toxin producing E. coli. And next, it's good to check the news once in a while. Just Google outbreaks, see what the current diseases everyone is thinking about are, like the McDonald's E. coli outbreak.
Yeah, so here's some resources that can be helpful. So the history of epidemiology page on the CDC has a lot of good information about some of the big figures in epidemiology that you'll see. CIDRAP is based at the University of Minnesota, which I'm kind of biased for because I'm from Minnesota, but they have a lot of good infectious disease reporting. So if you want to keep up on outbreaks, that's a good option. Same with MMWR, that's ran by the CDC. And you can also look at the CDC textbook. Honestly, that's probably one of your best resources. It has so much good information there. It is a very long textbook, so I recommend just like looking through the stuff that you're confused about and reading through that, but super useful. Also, the SciOly wiki and the test exchange are super good resources if you're looking for extra information.
Yeah, thank you so much. And we have a little bit of time for questions if you guys want to ask us anything. I will probably stop sharing for now. Okay, let's see. Oh, I see there are questions. Okay, someone had a question on noroviruses. So you probably heard their common name, which is stomach flu. That's what the norovirus is. And it's interesting because I think one way norovirus can spread is that if someone throws up, the particulates through the air can actually spread very, very far and then give other people in the room norovirus.
Yeah, they also have a very low incubation time, which is interesting. But yeah, I think they're saying that as like a possible answer to the retroviruses thing, the other group. I don't know if there is a term for the other group that isn't retroviruses.
Oh, I
I think
see.
it's just retroviruses and the rest of them. Maybe there is. I'm not super sure.
Let me see. Retroviruses versus retrovirus is a type of virus. I'm just looking at Wikipedia right now. What are the types of virus?
Yeah, because I feel like retroviruses are a pretty small subset of viruses in general.
That's true. Yeah, I don't think there's a term for the other kind. Okay, we'll just call them retroviruses and the other ones.
Yeah. Ooh, okay. When do you use odds ratio versus relative risk? So this is pretty much completely up to the study that you did. So odds ratio you will only use in a case control study, and relative risk you will only use in a cohort study. So if you want to just memorize that, that will get you most of the way with these questions. The reason you don't use relative risk on those case control studies is we don't have any information about the population at large when it comes to how many people are actually exposed and at risk and diseased. So we can't use the relative risk for case control. So case control, always odds ratio, and cohort study, always relative risk. So if they ever ask you to do like whatever the best correlation is, just look at the type of study and decide off of that.
I know there's like another workshop going on. If you guys have to go to that, feel free. We'll probably like stay on a little bit longer to answer questions.
And you choose which one you want to use if it just gives the table slash something like the table. Uh, if they're asking you to use like, if they're not giving you the information, then I'd say it's a poorly written question. You shouldn't need to guess between them. So if you just get the table, like the one I showed in the presentation, that was kind of purposefully ambiguous, so we can look at it as a case control study and then separately as a cohort study, right? So if they're asking you to determine which one to use between those two, they should really also be giving you the information of what type of study it is, because otherwise you don't really know.
Although sometimes they will like ask you to determine which is the best type of study to use, and then you have to go off that.
Yeah,
It's like it's a little bit double jeopardy, but I know some tests do that.
yeah, but if you don't have information about the type of study and it's asking you to choose between them, it's just a bad question. Let's wait like a minute longer to see if there's any extra questions. And then I
Yeah.
think it's fair to end the meeting.
Yes, and I think people can ask question on like the Microsoft Teams thing. Oh yes, we will be the. I think the SciOly GT will be sending the slides out.
Yeah, they should be on the Teams. I'm pretty sure there's a channel for that. So if you add that channel, you should be able to see it.
And I think we're going to be answering questions on the teams as well. It might take us some time, but we'll get around to it.
Yeah. There's a help channel in the teams. So if you have any questions that come up afterwards about disease detectives, just throw it in there, and one of us will probably answer when we see it.
Great. I think we are probably done. I don't see any more new disease-related questions. Yeah, thank you guys so much for coming. We hope that you learned something from this.
Yeah, thank you. This is my favorite event. Disease Detectives is very cool. So I highly recommend you continue trying to learn it and maybe consider learning more about epidemiology. It is all very, very interesting.
Good luck on all your competitions this year.